Hello students, this is part 2 of chapter 2, and if you've ever had trouble with resonance structures or never got them, never understood the rules, this video is for you. So I'm going to talk about resonance structures, what they really are, the rules in drawing them, how to draw them, and how to determine the major contributors, which ones are lower or higher in energy than others. So first of all, resonance structures are not real structures. These are imaginary constructs. They're basically used to show electron movement within a molecule. They're a tool to understand the reactivity of the molecule, just like you saw in the previous video. Molecules and their resonance structures, also called forms, should be thought of as a weighted average of all of those structures. So if I look at formic acid here, I can draw several structures, and they may not be the best looking structures, but I can draw several structures that can show the bonding. So notice I keep the skeletal framework the same, the single sigma bond skeletal framework the same, but I can move around lone pairs, basically the pi bond electrons. I can take the pi bond and this double bond and move it up as a lone pair and get to this structure. I can take this lone pair here, form a bond here, and get to this third structure. So these are just our way to explain reactivity. None of these structures exist. The molecule is actually a blend of all of these. This one is the best one because all octets are filled and there are no charges. This is the worst because the carbon octet is not filled. It only has 6 electrons and a plus formal charge. This one has the octets filled, but there are charges. So all of these contribute to the overall blended hybrid structure, but it's mostly character of this major guy, the lower energy one. So while the structures may be different, for example, each resonance form could be, for example, this blue horse or this red donkey or some other animal, but overall there's only one molecule and it's a perfect blend or a weighted average blend of all of them. In this case, with the blue horse and red donkey, you get a purple meal. Okay, so overall, if I blended this whole molecule, I could draw a structure where you have some double bond character here. So maybe I put like a little bit of a double bond here, dashed line, and then it's mostly a double bond, but still maybe partially dashed here, maybe 1 3/4 of a bond here. Okay, here are the rules. Only electrons move, the ones in the pi system, lone pairs and p orbitals. That's why these orbitals are key to understand. Structures need to be valid Lewis structures. So carbon can never have 5 bonds, but it can have 3 bonds and no lone pairs with a formal charge of 1. That's what we saw in the previous slide. Keep track of lone pairs and formal charges, draw those. Use curved arrow notation. This will help a lot to track electron movement and help you draw other resonance forms. We use a double-headed arrow between forms and a bracket around the entire set. And the overall charge of the molecule is the same for each structure. The lowest energy forms are the major ones and contribute most to the overall structure. How do you know what's the lowest energy one? These are 3 key ways you could figure that out. The most important one, this is in order of importance, is fulfilling octets. So CNOF, they want 8 electrons. If I look at the formic acid resonance structures, 1 and 3 are better than the middle one because the middle one does not have a full octet. The other key thing is putting negative charges on the more electronegative atom. So you draw the correct Lewis dot structures, but then when you're determining energy, look, we don't have this example here, but if you had a structure where the negative charge is on an O instead of an N, O is more electronegative. So the one with a negative charge on the O would be better, more major, lower in energy. The next is neutral is better. You want to minimize charges or minimize the separation by distance of those charges. So look at this. Overall, 1 is neutral. It's better than 2 and 3. But look at 2 versus 3. If I just looked at charges, these are further apart. These are closer, but the bigger, more dominant effect is fulfilling octet. So no matter what, because the center one does not fulfill octet, this is still better. The other thing is sometimes you're forced to draw structures where you have a +2 or -2 formal charge. That is always worse than structures with +1 or -1. And obviously 0 is the best. When you draw resonance forms or structures, you need to look for pi bonds or double bonds, same thing, or lone pairs. So for example, 2 p orbitals make up a double bond. This XY here, showing 2 p orbitals overlapping in phase, these are the pi electrons here, is the same thing as this double bond. It's a multiple bond. The other thing is next door to it, Z should have 0, 1, or 2 electrons. So this Z could have 0, 1, or 2 electrons. 0 because then the pi electrons can go over here. 1 because maybe you could do a radical reaction, 1 from each can form a double bond here. Or 2 because then these 2 electrons can then go towards the double bond and move that pi bond on itself or somewhere else. So let's just go through that example. Here's a pentadienyl anion, meaning you have a negative charge on this carbon. This is now a carbanion. It has a full octet, but 1 is a lone pair here. You have a lone pair here, so a formal charge of -1. Since there's a double bond nearby, something that it can do is those 2 electrons, that lone pair can form a bond. It can form a pi bond, a double bond, and it'll become this. And then because carbon can't have 5 bonds, it has to kick up and break this double bond and force this pi bond, those 2 electrons, to go up as a lone pair to create this. So going from left to right, you get this structure. You go lone pair to bond and bond to lone pair. Now in the next structure, you could do a couple things. One, you could just take the lone pair, any of these lone pairs, to form another pi bond here. Then this pi bond needs to break, so it could go back to what it happened before, and it could put the electrons back on carbon. Or if there's something else nearby, it can go to this carbon to form a double bond, and then kick up the pi bond there as a lone pair. So here, it's interesting, you go lone pair to bond, but bond to bond, and then a bond to lone pair. Notice how the formal charges change. Pause this, review this if that didn't resonate with you this first time. And we're going to do more practice. Before practicing, let me tell you that resonance structures lead to stability of a molecule. The reason is that the electron density is spread out, or we say delocalized, across other atoms. That means they're closer to other nuclei in the molecule. The greater the resonance forms, the more the resonance forms, the more stable the molecule. Here's an example. Benzene is shown below. It has 3 double bonds. You could draw resonance structures where you just keep cycling the double bonds around the molecule. This actually creates a current. So you could show these 2. These don't separately exist. It's a blend where it's all circulated through like a current. So you never ever find a single bond or a double bond measured. You might expect to measure a single and a double bond, a longer and a shorter bond, but you don't. You only measure one type of bond in benzene, and it's about 1.5 bonds. So this is more stable than normal alkenes, which are organic compounds with double bonds. And you see that it's much less reactive. So it's more stable. It's not going to break the pi bonds to go react with other things. That's what tells us it's more stable, and it is because of this resonance. Just to let you know, this blend here, we also call that a hybrid. That's the hybrid structure that you could draw. Sometimes you'll see it as dashed lines, kind of indicating 1.5. Let's do our practice, and we're going to have more practice throughout the week. Here's our concept check. You guys are going to pause and do this, and then I'll go over it. Draw 2 other resonance structures for this structure below. This is a resonance form of a certain molecule. So there are 2 other ones. Use curved arrow notation to show the movement of electrons going from each structure. So draw a structure and then use curved arrow to show movement going from the left to the right structure, and then again from that center to the right one. And then at the end, identify the major and minor contributors. So make sure you try this before hearing my answer. The first structure I drew is, I did it stepwise. I noticed that this carbon is a carbocation. If you can't see that, just remember the bond line notation. This has 1 H. It doesn't have 2 H's off of it because then it wouldn't have a formal charge. It has 1 H. It only has 6 electrons, so it wants 2 more. It's going to grab 2 here. This pi bond is going to move, kind of like opening a book, the pages of a book. You're going to move over here, so you have a double bond now here. And what happens is, because this pi bond moved over here, now this carbon is deficient. Now this only has 6 electrons because it has the carbon, oxygen, hydrogen, but nothing else. So this now has a formal charge of plus. The next thing I can do is take a lone pair, any of these lone pairs, and form a pi bond to fulfill the octet. And that gives us this neutral major structure. So these are 3 valid resonance structures. Some of you may have done this all in one shot, move the lone pairs and kick this pi bond over in one shot to get you to the 3rd structure. That's totally fine. To show another structure, then you could just kick this up to give that center structure. This is major because all octets are filled. Here, the octets aren't filled. These are both minor. You could say that this might be slightly minor because the charges are farther apart, charge separation. Here, they're closer together. Charges, it takes energy to separate charges. So that's the answer to that. We'll do more practice later.